From space, our planet looks peaceful. Soft blues and whites, slow-moving clouds, the quiet curve of the horizon. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. But look closer. Somewhere on that surface, right now, something ancient and powerful is burning. A wildfire is moving through a forest, or a grassland, or a hillside thick with dry brush. It is not a disaster that came from nowhere. It is something this planet has known for a very, very long time. Wildfires are unplanned fires that burn in natural areas like forests, grasslands, and shrublands. They spread on their own, driven by wind and fuel and heat. They are not small. Some wildfires burn for weeks. Some burn across millions of acres. The largest wildfires in recorded history have covered areas bigger than entire countries. There is something humbling about that scale. A single fire moving across a continent. Smoke rising so high it enters the upper atmosphere. The glow visible from orbit. Scientists estimate that wildfires burn roughly 865 million acres of land across the Earth every single year. That number is almost too large to picture. Think of it this way. That is an area larger than the entire country of India, burning every year somewhere on this planet. Most of it happens quietly, far from cities, in places most people will never see. Fire is one of the oldest forces on Earth. The earliest evidence of wildfire in the fossil record goes back about 420 million years. That is long before the dinosaurs, long before most complex life on land. The moment plants began to cover the ground, fire followed. Because wherever there is dry fuel and oxygen and a spark, fire will find a way. That spark in nature most often comes from lightning. A single bolt strikes a dry tree on a hillside. The bark smolders. The wind picks up. And something begins that may not stop for weeks. Lightning causes a significant portion of all natural wildfires on Earth, especially in remote forests where no human ever walks. But fire is not simply destruction. That is the part that surprises most people when they first learn it. Fire is a process. It is something the land does, the way the ocean makes waves, or the sky makes rain. Many ecosystems, the communities of plants and animals that live together in a place, did not just survive fire over millions of years. They were shaped by it. They came to need it. The forests of the American West, the savannas of Africa, the eucalyptus woodlands of Australia. These places evolved alongside fire. Their soils, their seeds, their animals, their cycles of growth and rest. All of it developed in a world where fire came through regularly. Fire is woven into the biology of these places as deeply as sunlight or water. This is one of the great quiet truths of our planet. The things that seem most violent are often the things that make life possible. A wildfire tears through a pine forest, and the heat opens the sealed cones of lodgepole pines, releasing seeds that would never have fallen otherwise. The ash left behind is rich with minerals. New plants grow faster in burned soil than in unburned soil. The forest does not end. It begins again. That cycle, burning and regrowing, has been running on this planet for hundreds of millions of years, long before humans arrived, long before anyone was here to watch. And yet, we are here now, and we watch. We study these fires with satellites and sensors. We track their heat signatures from space. We measure the smoke they send into the sky and follow it as it drifts across oceans. We have learned an enormous amount about what fire does, how it moves, what it needs, and what it leaves behind. Over the next few hours, we are going to follow that fire together. We will start with the simple chemistry of how a flame is born. We will move through the wind and the hills and the dry summer heat that turns a spark into something vast. We will visit the animals that run and the ones that stay. We will go underground, where fire changes the soil in ways that last for centuries. And we will end, as fire always does, with something new growing in the quiet ash. Close your eyes if you like. Let the story come to you. There is so much to see. Fire is one of the oldest things on Earth, but at its heart, it is remarkably simple. Every fire that has ever burned, from a candle flame to a wildfire sweeping across 1,000,000 acres, needs exactly 3 things: It needs fuel, it needs heat, and it needs oxygen. Remove any one of those three, and the fire dies. That is it. That is the whole secret. Scientists call this the fire triangle, and it is the foundation for everything we will talk about tonight. Let's start with fuel. Fuel is anything that can burn. In a wildfire, that means grass, leaves, pine needles, shrubs, and trees. Dead wood burns faster than living wood because living wood holds water inside its fibers. That water acts like a natural brake. It takes energy to boil that water away before the wood itself can catch. Dry, dead wood has no such protection. It ignites quickly and it burns hot. After a long drought, even living trees can dry out enough to burn easily. Their leaves turn brittle. Their bark cracks. The whole forest becomes something closer to kindling. Now think about how much fuel a forest can hold. A single acre of dry grassland might carry 2 tons of burnable material. A dense pine forest can hold 10 times that. All of it waiting, all of it patient. Heat is the second piece. A fire needs enough heat to raise its fuel to what scientists call the ignition temperature, the exact point at which a material will catch and start burning on its own. For dry wood, that temperature sits somewhere around 300 degrees Celsius, which is roughly 570 degrees Fahrenheit. That is about 3 times hotter than the hottest setting on most kitchen ovens. Once fuel reaches that temperature, it releases gases. Those gases mix with the air around them, and those gases are what actually burn. The flame you see above a burning log is not the wood itself on fire. It is those released gases glowing as they combust. That brings us to the third piece, oxygen. Air is about 21% oxygen. That is just enough to sustain a fire beautifully. If oxygen levels dropped even a few percentage points, fires would struggle to burn at all. If they rose much higher, almost everything on Earth would be dangerously flammable. The planet has held this balance for a very long time. Scientists who study ancient air trapped in ice and rock believe oxygen levels have shifted over hundreds of millions of years. And those shifts changed how fire behaved across the whole planet. More oxygen meant more fire. Less oxygen meant less. the air itself sets the rules. When all three pieces come together, something remarkable happens. The fuel releases gases. Those gases react with oxygen. That reaction produces heat, and that heat ignites more fuel, which releases more gases, which react with more oxygen. The fire feeds itself. It becomes its own engine. Scientists call this a chain reaction, a loop where each step powers the next. A wildfire is not just burning. It is a self-sustaining chemical process, running as long as it has what it needs. This is why firefighters focus so hard on breaking the triangle. They drop water and fire retardant on burning trees to cool the fuel below ignition temperature, attacking the heat. They cut fire breaks, long strips of cleared land with no trees or brush, to starve the fire of fuel. Sometimes they even use controlled burns ahead of an advancing fire, burning the fuel away before the wildfire can reach it. Each strategy targets one corner of that triangle. Take away one corner, and the whole thing collapses. There is something almost elegant about this, a force that can consume thousands of acres, that can be seen from space, that can change the shape of a mountain, rests on three simple needs: fuel, heat, oxygen. It is the same three things whether the fire is a small campfire crackling on a cold night, or a crown fire roaring through the tops of 100-foot-tall trees at 60 miles an hour. The triangle does not care about scale. It only cares that all three pieces are present, and in the right conditions, in a dry summer, in a forest full of dead wood, with a hot wind pushing across the hills, all three pieces come together very easily. The fire does not need much of an invitation. A single spark is enough, sometimes even less than that, which brings us gently to where wildfires actually come from. How that first spark finds its way into the world, and how something so small can become something so vast. Most wildfires are started by people, not always on purpose, not always through carelessness, but the numbers are clear. In the United States, roughly 85 out of every 100 wildfires trace back to a human cause. A campfire left smoldering, a cigarette tossed from a car window, a power line swaying in the wind until it brushes a dry branch. The is more than enough to ignite dead vegetation. The 2018 Camp Fire in Northern California, one of the deadliest in the state's history, was traced to a faulty transmission line. A single piece of aging equipment on a dry November morning. The fire that followed killed 85 people and burned nearly 200,000 acres. It is a quiet reminder of how much weight a single moment can carry. Sparks from machinery are another source. A chainsaw cutting through a rocky patch of ground. A lawnmower blade striking a stone. Even a train wheel grinding against a rail on a hot, dry afternoon. Each of these creates a small burst of heat. Most of the time, nothing happens. The spark lands on bare dirt or damp grass and dies before it can do anything. But on the wrong day, in the wrong conditions, that tiny burst of heat lands on a dry leaf or a patch of dead grass or a curl of bark, and something begins. Campfires that are not fully put out are responsible for a surprising number of wildfires each year. A fire that looks cold can still hold heat deep in its ash bed. Wind can stir those coals back to life hours later, or even the next morning. The rule for putting out a campfire properly is to drown it, stir it, and drown it again until the ash is cool enough to touch with a bare hand. Many fires that start from campfires were never meant to escape. They simply were not finished. Then there is lightning. About 15 out of every 100 wildfires in the United States are started by lightning strikes. In the American West and across parts of Canada and Australia, lightning is the dominant natural ignition source. A single thunderstorm can drop dozens of strikes across a dry forest in a matter of minutes. Some of those strikes start fires that smolder quietly for days before the wind picks them up and carries them somewhere they can grow. These lightning-caused fires tend to start in remote places, far from roads and towns, which means they can burn for a long time before anyone notices them. Lightning fires have been starting in forests for hundreds of millions of years, long before humans walked the earth. Lightning was already doing this work. The charcoal left behind in ancient rock layers tells us that fire has been part of the land's story for a very long time. In that sense, fire is not an invader, always been part of how forests breathe and reset themselves. Volcanic activity can also start wildfires, though this is far less common. Lava flows that move into dry vegetation, or volcanic ash that lands hot enough to ignite dry material, can set off fires in the areas surrounding an eruption. These fires are rare, but they are a reminder that the Earth itself carries heat close to its surface, and that heat is always looking for a way out. There is also a category of fire that scientists call spontaneous combustion. This happens when organic material, things like rotting leaves, damp hay, or decomposing wood, generates its own heat through the slow process of decay. Under the right conditions, that internal heat can build until it reaches ignition temperature. It sounds almost impossible. A pile of leaves catching fire from the inside. But it happens. It is slow, and it requires specific conditions, but it is real. What all of these causes share is the same basic truth. The fire does not create itself. It waits. It waits for a source of heat to arrive, and for the fuel and oxygen that the previous section described to be in place. The source of ignition is just the final piece. The land, the weather, the season, the years of accumulated dry wood and dead grass, all of that is already waiting. The spark is just the signal that the waiting is over. Once the spark arrives, the fire begins. But whether it stays small or grows into something vast depends heavily on what the air is doing. Wind is not just a background condition. It is one of the most powerful forces shaping how a wildfire behaves, where it goes, and how quickly it gets there. Think of wind as the fire's partner. It brings oxygen, and fire needs oxygen the way a living thing needs air to breathe. A calm, still day gives a fire just the oxygen that surrounds it. But when wind moves across the land, it delivers a constant, fresh supply. It fans the flames the way you might blow on a small ember to coax it back to life. The more oxygen arrives, the hotter and more intense the fire becomes. Wind does something else too. It dries out the fuel ahead of the fire. As warm, moving air passes over grass and leaves and branches, it pulls moisture from them. Scientists call this process desiccation, which simply means drying out. can become brittle and ready to burn within hours if a dry wind moves through. The fire has not even arrived yet, and the wind is already preparing the land for it. There is also the matter of direction. Wind tells a fire which way to go. A fire burning in still air tends to spread slowly in all directions, like a circle growing outward. But a steady wind pushes the fire in one direction, creating what firefighters call a head fire. The head of the fire, the edge moving into the wind's direction, burns hotter and moves faster than any other part. It is the most dangerous edge. The sides of the fire, called the flanks, move more slowly. The back of the fire, moving against the wind, is the slowest and coolest part of all. Wind speeds matter enormously. A gentle breeze of 10 miles per hour behaves very differently from a gusting wind of 40 or 50 miles per hour. In strong winds, burning embers lift off the fire and travel through the air. These embers, sometimes called firebrands, can land hundreds of yards or even miles ahead of the main fire. When they land on dry fuel, they start new fires. Scientists call these spot fires. A single wildfire can produce thousands of spot fires ahead of its main front, making it nearly impossible to contain. The fire is no longer just a line moving across the land. It is everywhere at once. Some of the most destructive wildfires in history have been driven by a specific kind of wind. In California, these are called the Santa Ana winds. They form when high pressure builds over the dry interior of the western United States, and air rushes downhill toward the coast. As that air descends, it compresses and warms. It arrives at lower elevations hot, dry, and fast. Wind speeds during Santa Ana events can exceed 60 miles per hour. These winds have driven some of the most damaging fires in California's recorded history. Similar winds exist in other parts of the world. In Australia, they are called the Diablo winds in some regions, and the country has its own version of these dry, descending gusts that have fueled catastrophic fire seasons. There is something almost ancient about the connection between wind and fire. Long before humans walked the earth, wind was shaping how lightning-caused fires moved across forests and grasslands. The land land evolved alongside this force. Some grasses grow low and flexible, bending in the wind rather than breaking, which helps them survive the fires that wind drives across open plains. Some trees grow thick, corky bark that resists heat. These adaptations did not happen by accident. They are the result of millions of years of fire and wind working together, and life finding ways to endure. Wind also carries fires, effects far beyond the flames themselves. Smoke, ash, and tiny particles rise into the air and travel on the same currents that fed the fire. A wildfire burning in one state can send smoke drifting across an entire continent. The seeds of certain plants ride the wind into burned clearings, arriving just in time to take root in the newly opened soil. Even the carbon released by the fire enters the atmosphere and begins its long movement through the global systems that regulate the planet's climate. Wind is invisible. You cannot hold it or see it. But in the story of a wildfire, it is everywhere. It is the force that turns a small flame into a moving wall of heat. It is the messenger that carries the fire's reach far beyond its source. It is, in many ways, the fire's most faithful companion. Now imagine the fire has found its wind. It is moving, and beneath it, shaping every step it takes, is the land itself. Terrain, the shape of the ground, its hills and valleys, and steep rocky slopes, controls a wildfire just as surely as wind does. Most people think of fire as something that simply spreads outward in all directions. But fire is not that simple. It reads the land. It follows the land. And on certain kinds of ground, it can move in ways that seem almost impossible. The most important thing terrain does is change how fire climbs. Fire moves faster uphill than it does on flat ground. This is one of the most well-established facts in fire science, and it matters enormously to the people who fight wildfires. When a flame burns on a slope, the hot gases and heat it produces rise naturally upward. Those rising gases preheat the fuel above the fire, the dry grass, the shrubs, the trees, before the flame even arrives. The fuel above is already warm and ready to burn. So the fire climbs quickly, almost eagerly, something being pulled toward the top. The steeper the slope, the faster this happens. Scientists have found that for every 10 degrees of added slope, a fire can roughly double its speed. A fire moving at a slow walk on flat ground can become a sprinting wall of flame on a steep hillside. Firefighters know this well. They are trained never to position themselves above an active fire on a slope, because the fire below them is always moving upward, always moving toward them. Valleys and canyons add another layer of danger. When a fire burns inside a narrow canyon, the canyon walls funnel the heat and the wind into a tight channel. The air has nowhere to go but forward. This creates a kind of natural bellows, a device that forces air into a flame to make it burn hotter. And the fire inside a canyon can accelerate to terrifying speeds. Some of the most deadly wildfires in history have occurred in steep, narrow terrain where fire raced uphill through a canyon faster than people could run. There is a phenomenon called a fire whirl, sometimes called a fire tornado, that terrain can help create. When hot air rises rapidly from a fire and meets cooler air above it, the air can begin to spin. If the terrain channels this spinning air, the rotation tightens, just like a figure skater pulling in their arms. The result is a rotating column of flame that can reach hundreds of feet into the sky. Fire whirls can carry burning debris far ahead of the main fire, starting new fires in places the main blaze has not yet reached. Ridgelines, the long, narrow tops of hills and mountain ranges, create their own fire behavior. Wind speeds up as it crosses a ridge, compressed and accelerated by the shape of the land. A fire climbing toward a ridgeline often surges in speed as it nears the top, driven by that accelerating wind. Once it crests the ridge, it can drop down the other side and begin the whole process again on a fresh slope, full of unburned fuel. Saddles the low dips between two higher points on a ridge act like funnels for wind. Air rushing across a landscape naturally flows through the lowest available gap, just as water finds the easiest path downhill. A fire near a saddle can be pulled through that gap with sudden force, changing direction and speed in ways that can catch even experienced firefighters off guard. shaped partly by where fires have and have not been able to travel. The shape of a hillside, the direction it faces, whether it catches morning sun or stays in afternoon shade. All of these things affect how dry the fuel becomes and how readily it burns. A south-facing slope in the northern hemisphere gets more direct sunlight. It is warmer and drier. It burns more easily than the shadier slope just across the valley. Terrain does not move. It does not change from day to day, but it shapes every fire that crosses it in deep and lasting ways. The hills and valleys of a landscape are like a set of instructions that a fire follows without knowing it. The land tells the fire where to go fast, where to slow, where to leap, and where to stop. Fire listens to the land the way water does, finding the path of least resistance, following the shape of the earth beneath it. But the land is only part of the story. Above the land, the sky has its own say. And sometimes, the sky is the most powerful force of all. Weather shapes fire the way a conductor shapes an orchestra. Every instrument plays its part. Heat, drought, and humidity all work together or against each other to decide whether a spark becomes a small brush fire or a monster that swallows whole mountain ranges. Start with heat. On a hot day, the sun bakes the ground and everything on it. Dead leaves curl. Fallen branches dry out from the inside. Grasses turn from green to gold to brittle brown. When air temperature climbs above 90 degrees Fahrenheit, fuel dries out much faster than it can absorb moisture from the air. Scientists call this process curing, the same word used for drying meat or aging cheese. The fuel is essentially being preserved in a state that is perfect for burning. A forest floor that holds some moisture on a mild spring day can become a bed of tinder by midsummer. The difference between those two conditions can be a matter of weeks. Now think about drought. A single dry day does not make a wildfire season, but weeks and months without rain build something dangerous. Soil loses its moisture. Tree roots pull water from deeper and deeper underground. Eventually, even living trees begin to dry out from the outside in. Their bark cracks. Their needles lose their natural oils. They stop being green shields against fire and start becoming fuel themselves. In a severe drought, a forest that once resisted fire can become one of the most flammable places on Earth. California's drought conditions in the early 2020s left millions of trees so dry that scientists measured their moisture content at levels close to kiln-dried lumber. The kind of wood used to build houses. That comparison is worth sitting with for a moment. Kiln-dried lumber is wood that has been baked in an industrial oven specifically to remove moisture before construction. When living trees reach that same level of dryness, an entire forest begins to behave like a stack of firewood. The scale of that is hard to hold in your mind. Imagine a stack of firewood the size of a mountain range. That is what a drought-stricken forest can become. Then there is humidity, the amount of water vapor floating in the air around us. Humidity is invisible, but it is one of the most powerful controls on fire behavior. When humidity is high, fuel absorbs moisture from the air itself. Even dry grass will pull a little water from humid air and become slightly harder to ignite. When humidity drops below about 25%, that protection disappears. Below 15%, fire behavior becomes extreme. Flames grow taller. Fire spreads faster. Embers travel farther on the wind. Firefighters track humidity the way sailors track tides. It tells them what the day is going to bring. There is a specific combination of conditions that fire weather scientists watch for with great care. They call it a red flag event. A red flag warning goes out when three things align at once: low humidity, high temperatures, and strong winds. Any one of those conditions makes fire more dangerous. All three together create the kind of day when a single spark can grow into a catastrophe within hours. On red flag days, fire crews go on high alert. Campfires are banned. Power companies sometimes shut off electricity to prevent downed lines from igniting dry grass. The relationship between drought and wildfire is also a loop that feeds itself. A large wildfire removes the trees and plants that once held moisture in the soil. Without that cover, rain runs off quickly instead of soaking in. The ground dries out faster the next season. The conditions for the next next fire arrives sooner. One drought and one fire can make the land more vulnerable to both for years afterward. This is the quiet arithmetic of fire weather. It is not dramatic in the way a wall of flame is dramatic. It is slow and steady and patient. Heat builds over weeks. Drought deepens over months. Humidity drops on a single dry afternoon. And then the conditions are simply right. The way a lock opens when all the tumblers fall into place at once. The sky and the land have been having this conversation for as long as forests have existed. Heat and moisture, wet years and dry years, cool seasons and scorching ones. They cycle through in patterns that stretch back millions of years. Fire has always been part of that cycle. It has always been waiting for the right weather to arrive. When the right weather finally arrives and the fire begins to move across the land, it does not look like one single thing. It looks like many things at once. A wildfire has different parts, each doing something different, each burning in its own way. Scientists who study fire give names to these parts. Together, they form what researchers call the anatomy of a wildfire, the structure of a living, moving blaze. The front edge of a wildfire is called the head. This is the leading edge, the part of the fire that is moving fastest and burning hottest. The head pushes forward in the direction the wind is blowing. It is the most dangerous part of any wildfire. Flames at the head can reach enormous heights. They lean forward like something in a hurry, tilted by the wind, orange and gold, and white at their brightest core. The heat coming off the head is intense enough to be felt from a great distance. Firefighters always track where the head is moving. Behind the head, on either side, the fire spreads outward in two long arms. These are called the flanks. The flanks move more slowly than the head because the wind is not pushing them directly forward. They burn lower and with a little less fury, but they are still dangerous. If the wind shifts direction, a flank can suddenly become a new head, racing off in a direction no one expected. Watching the flanks is part of how firefighters read a fire in real time. At the back of the fire, the part that is moving away from the wind, sits the heel. The heel burns slowly creeps along the ground, consuming fuel that the head and flanks have not yet reached. The heel is cooler and quieter. It does not command attention the way the head does, but it is still fire, still consuming, still leaving its mark on everything it touches. Now imagine floating above all of this and looking down. The shape of a wildfire from above is often described as an oval or a teardrop. The pointed end of that teardrop is the head, pushing forward. The wide, rounded back is the heel. The two long sides are the flanks. This shape is not random. It is the direct result of wind and fuel and terrain working together to create a predictable geometry. Fire scientists use this shape to predict where a fire will go next. Inside that oval, the ground tells its own story. The area the fire has already passed through is called the black. It is exactly what it sounds like. The soil is dark and bare. The trees that still stand are charred, their bark cracked and peeling, their branches stripped of leaves. The ground is covered in ash, pale gray and soft, almost like powder. If you could walk through the black in the hours just after a fire passed, the ash would rise in small puffs around your feet. The air would smell sharp and heavy. The silence would be striking. No insects, no birds, no rustling leaves, just the faint ticking sound of cooling wood. At the very edge of the fire's active burn, where the flames are meeting unburned fuel for the first time, something remarkable happens. The heat moving ahead of the flames begins to dry out the vegetation before the fire even arrives. This zone of preheating is invisible, but it is doing critical work. It is preparing the fuel, pulling moisture out of leaves and grass and bark, making them ready to ignite the moment the flame front reaches them. The fire is essentially preparing its own path forward. Above the fire, a column of smoke rises into the sky. This column can reach extraordinary heights. In a large, intense wildfire, the smoke column can climb 6 miles or more into the atmosphere. From a distance, this column is often the first thing people see. It starts white or pale gray near the base, where moisture from burning vegetation is mixing with the smoke. Higher up, it turns darker, thick and brown and heavy with particles. On a clear day, a large where the fire is hottest, near the center of the most intense burning, the flames can appear almost white. At the edges, where the fire is cooler and the fuel is running thin, the color deepens to a dull red. The fire is painting the world in every shade between gold and ash, moving and changing with every gust of wind. And beneath all that color and light, there is something that surprises almost everyone who learns it for the first time. Wildfires move. They move with a speed and purpose that feels almost alive. Most people imagine a wildfire creeping slowly through the trees, giving plenty of time to escape. The truth is far more startling. On flat, open ground with moderate wind, a wildfire can move at roughly 14 miles per hour. That is faster than most people can run. A healthy adult sprinting at full speed covers about 12 miles per hour. The fire is already ahead of them. This is one of the reasons wildfires are so dangerous, even when they are first spotted. By the time someone sees the smoke and understands what is happening, the fire may already be closer than it looks. But flat ground with moderate wind is not the worst case. Not even close. When a wildfire reaches a steep slope, something remarkable and terrifying happens. The fire accelerates. It doubles in speed, then doubles again. Scientists have measured wildfires moving up steep hillsides at speeds exceeding 35 miles per hour. That is fast enough to outrun a horse at full gallop. The reason goes back to the way heat rises. As the fire climbs, it preheats the fuel directly above it. The slope acts like a ramp, tilting the flames forward into fresh, dry grass and brush. The steeper the hill, the faster the fire feeds on what is waiting above it. Grass fires move fastest of all. In open grassland, with strong winds pushing from behind, a fire can race across the land at speeds of up to 70 miles per hour. That is highway speed. 70 miles per hour across an open field, consuming everything in its path. These grass fires are among the most dangerous wildfires on Earth precisely because they offer so little warning. The fuel is low to the ground. The flames are not always tall, and the speed is almost impossible to believe until you have seen it. There is a specific type of fast fast-moving fire that firefighters fear above almost everything else. It is called a blow-up. A blow-up happens when a fire suddenly and violently increases in intensity. Wind shifts, or a new source of fuel ignites, or the fire's own smoke column collapses back down onto the burning area. In seconds, a manageable fire becomes something else entirely. The heat surges. The flames leap. The fire can double or triple in size in under a minute. Blow-ups have killed experienced firefighters who had done everything right. The fire simply changed faster than anyone could react. One of the most studied blow-ups in history happened in 1949 in a place called Man Gulch in Montana. A small crew of smoke jumpers, firefighters who parachute into remote areas to fight fires, were caught when the fire below them blew up and raced up the slope. The fire moved so fast that most of the crew had no chance. 13 men died. The tragedy led to decades of research into how fires accelerate and how terrain and wind combine to create sudden, deadly speed. That research has saved many lives since. The speed of a wildfire is not constant. It pulses and breathes. When the wind drops, the fire slows. When the wind gusts, the fire surges forward. Firefighters track these rhythms carefully. They watch the smoke. They watch the flame height. They watch the way the fire's edge moves, whether it is creeping or running. A fire that is creeping can be managed. A fire that is running demands immediate retreat. There is something else hidden inside a fast-moving fire that most people never consider. The fire does not move as one solid wall of flame. It moves in fingers and lobes, irregular shapes that push forward faster in some places than others. These fingers can wrap around obstacles, curl around ridges, and suddenly surround an area that seemed safe just moments before. Firefighters call this flanking. A fire that appears to be moving away from you can send a finger around your position without warning. All of this speed, all of this unpredictable movement comes from the same forces that have always driven fire. Heat, fuel, and wind working together in patterns that are deeply complex. Scientists use satellite data, weather sensors, and computer models to try to predict where a fire will go and how fast it will get there. The models have grown remarkably accurate, but fire, in the end, still holds surprises. It moves through the world on its own terms, shaped by forces that go all the way down into the soil and all the way up into the sky above. Fire has been part of this planet for a very long time, not just decades or centuries. We are talking about hundreds of millions of years. Scientists have found evidence of ancient wildfires in rocks and coal deposits that are more than 400 million years old. Back then, the land looked nothing like it does today. The forests were strange and alien, full of giant ferns and towering mosses. But fire was already there, burning through them, shaping them, just as it shapes our forests now. This is one of the quietest and most important truths about wildfire. It is not a disaster that arrived recently. It is an ancient force that forests grew up alongside. Over millions of years, plants and trees did not simply endure fire. They adapted to it. They built their lives around it. The relationship between fire and forest is one of the oldest partnerships on Earth. Think about what that means. For hundreds of millions of years, fire has been clearing dead wood, returning nutrients to the soil, and opening up space for new growth. Forests that experience fire regularly are not damaged forests. They are forests in the middle of a very old cycle. The fire is not breaking the system. The fire is part of the system. Scientists who study this relationship have a name for it. They call it the fire regime. A fire regime is simply the pattern of how often fires burn in a given place, how large they tend to get, and how intense they usually are. Different forests have different fire regimes. A dry pine forest in the American West might burn in low, creeping ground fires every 5 to 15 years. A wet rainforest might go centuries between fires. A grassland might burn almost every year. Each of these patterns shaped the plants and animals that live there over thousands of generations. In forests with frequent, low-intensity fire regimes, the trees learned to survive small fires. They grew thick, fire-resistant bark. They lifted their lowest branches high off the ground, out of reach of ground-level flames. They dropped their seeds in ways that took advantage of the open, ash-rich soil that fire leaves behind. These trees are not victims of fire. They are fire's partners. When fire is removed from a forest that evolved with it, something unexpected happens. The forest does not simply thrive. It changes in ways that can make it more dangerous. Dead wood and dry leaves pile up on the ground year after year, with nothing to clear them away. Shrubs and small trees crowd in beneath the canopy. The forest becomes dense and full of fuel. When fire finally does arrive, it finds far more to burn than it would have found in a healthy, fire-adapted forest. The result is often a much larger, much hotter fire than the land ever experienced before. This is one of the great lessons that fire scientists have learned over the past century. For much of the 1900s, fire suppression, which means stopping and preventing fires as quickly as possible, was the standard approach to wildfire management in many countries. The goal seemed logical. Fires destroy trees, homes, and lives. Stop the fires. But the forests kept their accounting. Every year without fire was a year of fuel building up. The debt grew quietly in the underbrush. Researchers now understand that many forests need fire the way a meadow needs rain. It is not a threat to be eliminated. It is a process to be understood and, where possible, carefully guided. The science of fire ecology, the study of how fire interacts with living systems, has grown enormously over the past few decades. What it keeps revealing is the same thing, again and again. Fire is woven into the fabric of life on land in ways that go far deeper than anyone first imagined. There is something deeply calming about this if you sit with it for a moment. The forests you see today, the tall pines, the spreading oaks, the eucalyptus groves with their papery bark, did not appear by accident. They were shaped by fire across thousands of years. Every thick-barked trunk, every high-lifted branch, every seed that germinates best in scorched soil carries the memory of ancient flames. The forest is not afraid of fire. The forest remembers fire. It has been preparing for it and recovering from it and preparing again in a slow and steady rhythm that stretches stretches back far beyond any human memory. Fire does not just burn through the forest. Over time, fire and forest build each other. That is the cycle, and it has been turning quietly and steadily for longer than our species has existed to watch it. Some trees do not merely survive fire, they depend on it. This is one of the quieter wonders of the natural world. Certain trees have grown so close to fire over so many thousands of years that they have built fire into their very design. They do not just tolerate flames, they wait for them. They need them. Without fire, these trees cannot complete their life cycle. Without fire, their seeds stay locked away. Their forests grow crowded and dim, and the next generation never gets its chance. The lodgepole pine is one of the most striking examples. This tall, straight tree grows across vast stretches of western North America, from the Rocky Mountains up into Canada. Its cones are sealed shut with a thick, waxy resin. That resin acts like a lock. Under normal conditions, the cones stay closed for years, sometimes decades. But when fire sweeps through and the heat rises high enough, the resin melts. The cones open. Seeds pour out by the thousands onto the warm, ash-covered ground below. The fire that just burned the forest is also the force that plants the next one. This kind of cone is called a serotinous cone, meaning it opens only in response to heat. The lodgepole pine is not alone in having them. The jack pine, which covers enormous areas of Canada and the northern United States, uses the same strategy. So does the knobcone pine of California. These trees have made a quiet agreement with fire. They hold their seeds in reserve, sometimes for many years, trusting that fire will eventually come and prepare the ground for them. The ground fire leaves behind is, in many ways, ideal for a seedling. The ash adds minerals to the soil. The thick mat of old needles and dead plant matter that would otherwise block sunlight has been cleared away. Competing plants that might crowd out a young pine are gone. The seedling that sprouts in the weeks after a fire often has more light, more space, and more nutrients than it would have found in an unburned forest. Fire does not just open the cones, it sets the table. The giant sequoia, one of the largest living things on Earth follows a similar path. These enormous trees grow on the western slopes of California's Sierra Nevada mountains. Their cones can stay on the tree for 20 years or more without opening. A single mature sequoia can hold as many as 11,000 cones at one time. When fire comes, the heat dries the cones and opens them. One large fire can release millions of sequoia seeds in a matter of days. The seeds are tiny, each one no bigger than a flake of oatmeal, but they fall onto bare, fire-cleared mineral soil. And in that warm and open ground, some of them take hold. The oldest giant sequoias alive today, some of them more than 2,000 years old, began their lives exactly this way. A fire opened the way for them. The eucalyptus trees of Australia have their own relationship with fire. Many eucalyptus species carry their dormant buds deep beneath thick, protective bark. After a fire burns away the outer layers of the tree, these hidden buds, called epicormic buds, push through and sprout. A eucalyptus that looks completely destroyed after a fire can be covered in fresh green growth within weeks. The tree does not wait to regrow from a seed. It regrows from itself, from buds it has been keeping safe for exactly this moment. There is something almost patient about this. These trees do not panic when fire comes. They have been ready. The banksia, a flowering shrub and tree found across Australia, takes a similar approach. Many banksia species hold their seed pods closed for years. Fire opens them. Some banksia species actually need the smoke itself, not just the heat, to trigger germination. Chemicals in smoke signal to the seed that fire has passed and that the ground is ready. Scientists have identified one of these chemicals, a compound called carotenoid, found in the smoke of burning plant material. It acts like a wake-up call. The seed has been waiting, and the smoke tells it the time has come. These trees are not passive. They are not simply enduring fire. They have shaped themselves around it over millions of years, building strategies so precise and so reliable that fire has become part of their growth cycle. They are neighbors to fire in the truest sense, before the first human being ever struck a spark or watched a hillside burn. The forest does not fear what it has learned to use. And the animals know this too. Long before a fire crests a ridge or jumps a road, the creatures of the forest are already moving. Birds lift from the canopy in wide, sweeping flocks. Deer push through the underbrush at a pace they rarely keep. The air carries a signal that every living thing in the forest can read. Smoke, heat, the low, distant crackle that travels farther than most people expect. Animals have been reading these signals for millions of years, and their responses are as varied and precise as the fires themselves. Many animals simply run. Large mammals like elk, deer, and bears move fast and far ahead of an advancing fire front. They follow the same instinct that has kept their ancestors alive through countless fire seasons. Their legs carry them to rivers, to rocky outcrops, to open meadows where the fuel load is thin, and the fire cannot follow as easily. Speed is their strategy. Distance is their safety. But not every animal runs. Some go down. Ground squirrels and pocket gophers retreat into their burrows when fire approaches. Underground, the temperature stays far cooler than the surface above. A fire can burn across the top of a burrow system, while the animals inside remain unharmed. Scientists have measured soil temperatures just a few inches below the surface during a fire, and found that the heat barely penetrates. The earth itself becomes a shield. These small animals have not evolved to outrun fire. They have evolved to outlast it. Snakes and lizards use a similar strategy. They press into rock crevices, slide under stones, or burrow into loose soil. Their low body temperature and slow metabolism mean they need very little oxygen, which helps them survive in the smoky, low oxygen air that settles close to the ground during a burn. They wait, they endure, and when the fire passes, they emerge into a world that has changed around them. Some birds do something remarkable. Certain species, including several types of woodpeckers, are actually attracted to wildfires. The black-backed woodpecker in North America is one of the most well-known examples. This bird seeks out freshly burned forests with what scientists describe as striking speed and accuracy. It feeds on the wood-boring beetles that move into charred trees almost immediately after a fire. The burned forest is not a wasteland to this bird. It is a feast. The black-backed woodpecker has heat-sensing organs that may help it detect fires from great distances. Though scientists are still studying exactly how this works, what is clear is that this bird has built its entire life around burned forests. It nests in fire-killed trees. It raises its young there. Take away the fire, and you take away the bird's home. Insects respond to wildfire in ways that are just as striking. Some species of jewel beetles, a group of shiny, metallic insects, can detect the infrared radiation that a fire produces. Infrared radiation is a type of heat energy that travels outward from a fire in invisible waves. These beetles have small pit organs on their bodies that sense this radiation from miles away. They fly toward the fire, sometimes even into the active burn zone, to lay their eggs in the warm, freshly charred wood. Their larvae hatch into a world with almost no competition. Most other insects have fled or died. The burned wood is theirs alone. There are animals that seem almost indifferent to fire. The American black bear has been observed moving through the edges of active fires, apparently foraging. Bears are opportunistic, meaning they eat whatever is available, and a fire stirs up enormous amounts of food. Insects flee from the soil. Small mammals scatter. Berries and roots become exposed. A bear that knows how to move carefully along a fire's edge can find a remarkable amount to eat. And then there are the birds of prey. Hawks, falcons, and kites gather at the edges of wildfires in large numbers. They hunt the animals fleeing the flames. Mice, voles, rabbits, and lizards pour out of the burning vegetation, and the birds are waiting. Some researchers have documented what they call fire-following behavior in raptors, birds of prey, where the birds track the moving edge of a fire for days, feeding as they go. In Australia, certain birds of prey have even been observed picking up burning sticks and carrying them to unburned areas, apparently to flush out prey. Scientists call these birds firehawks, and their behavior suggests a level of awareness about fire is genuinely rare in the animal world. Every creature has its answer to fire. Run, hide, follow, wait, feed. The fire moves through, and life bends around it, finding every opening, every edge, every moment of stillness in the smoke. Below the surface, something quieter is happening. While the animals run and the birds circle, and the smoke rises in great dark columns, the fire is doing something most people never see. It is reaching down into the soil, into the dark, layered world beneath our feet. And what it does there is strange and subtle and worth slowing down to understand. Soil is not just dirt. It is a living system. A single handful of healthy forest soil contains billions of bacteria, millions of fungi, and thousands of tiny creatures too small to see without a microscope. There are thread-like structures called mycorrhizal networks, which are webs of fungal threads that connect the roots of trees to one another underground. These networks carry water and nutrients between trees, almost like a slow, silent form of communication. Scientists have found that trees can share sugars through these fungal threads, feeding neighbors that are struggling. The forest floor, in other words, is not just the bottom of the forest. It is part of the forest itself. When a wildfire burns, the heat travels downward, not as fast as it moves through the air, and not as dramatically, but it moves. The top layer of soil, called the litter layer, burns away almost completely. This is the loose mat of dead leaves, twigs, and fallen bark that covers the ground. Beneath that is the organic layer, darker and richer, full of decomposing material and living organisms. A moderate fire heats this layer significantly. A severe fire can heat it enough to kill most of the life within it. The temperature just 1 inch below the soil surface can reach over 200 degrees Fahrenheit during an intense burn. At 2 inches down, temperatures are lower, but still damaging. At 4 inches, the heat barely arrives at all. This means that the deeper the organism lives, the better its chances. Seeds buried deep in the soil often survive. Earthworms that move quickly downward can escape, but the thin, delicate fungal threads near the surface are often destroyed entirely. This loss matters more than it might seem. Those mycorrhizal networks take years to rebuild. Without them, young trees that sprout after a fire have a harder time finding water and nutrients. They are growing in a world where the underground support system has been damaged. Recovery at the surface depends, in part, on recovery underground. The two are tied together in ways scientists are still working to understand. Fire also changes the chemistry of the soil itself. When organic matter burns, it leaves behind ash. Ash is rich in minerals, particularly calcium, potassium, and magnesium. These minerals dissolve into the soil when rain arrives, making the ground suddenly more fertile. This is one reason why plants can grow back so quickly after a fire. The soil has been, in a sense, fertilized by the burning, but fire can also damage the soil's structure in a more lasting way. Intense heat causes the tiny particles in soil to fuse together, creating a hard, water-resistant layer just below the surface. Scientists call this a hydrophobic layer, which means a layer that repels water. Rain that falls on burned ground sometimes cannot soak in. Instead, it runs off the surface, carrying loose ash and soil with it. This is one reason wildfires can lead to mudslides and flooding in the weeks and months that follow. The ground, stripped of plants and sealed by heat, cannot absorb water the way it once did. And yet, even here, life finds a way through. Certain bacteria actually thrive in the aftermath of fire. They are adapted to the high mineral, low competition environment that a burned soil creates. They move in quickly, begin breaking down the ash, and start rebuilding the biological community from the ground up. Some of these bacteria fix nitrogen, pulling it from the air and converting it into a form that plants can use. They are, in a way, the first responders of the underground world. There are also fungi that specialize in burned ground. One group, called pyrophilous fungi, which means fire-loving fungi, appear almost exclusively in the months after a wildfire. They fruit quickly, releasing spores before other species can compete. Some of them are edible, and foragers have long known to search burned forests for morel mushrooms in the spring following a fire. The morel seems to sense the disturbance and responds to it, rising from the damaged soil like a recovery takes years, but it begins immediately in the dark, in the silence, in the slow and patient work of organisms too small to see. The surface of a burned forest looks, at first, like nothing at all. Black ground, gray ash, bare trunks standing like silent columns against a pale sky. To the eye, it seems like an ending. But scientists who have studied wildfire recovery know that the first days after a fire are among the most active and important in the entire cycle of a forest's life. For most of human history, people looked at a burned landscape and saw only loss. The early naturalists and explorers who traveled through fire-scarred land often described it in terms of ruin. They saw the blackened trees and the empty ground and assumed recovery, if it came at all, would take generations. It was a reasonable guess. It was also wrong. The shift in understanding came slowly, through careful watching. In the late 1800s and early 1900s, scientists began to stay in burned areas after the fire moved through. They came back the next week, the next month. They kept notes. What they found surprised them. Life did not wait. Life did not hesitate. Within days of a fire being extinguished, the burned ground was already changing. One of the earliest and most striking observations was the speed at which certain plants responded. Researchers noticed that some species seemed to sprout from the ash almost before the ground had cooled. These were not random survivors. They were specialists. Scientists came to understand that certain plants had evolved seeds that required heat, smoke, or chemical signals from ash to break dormancy. The resting state a seed enters while waiting for the right conditions to grow. The fire was not their enemy. It was their trigger. This discovery changed everything about how scientists thought about fire. For decades, the dominant view in forest management was that fire was purely destructive, something to be stopped at all costs. The early observations of post-fire recovery began to crack that idea open. By the mid-20th century, ecologists, scientists who study how living things interact with their environments, were starting to argue that fire was not an interruption of the forest's life. It was part of it. The first days after a fire are also when the land becomes most vulnerable to a different kind of damage. Rain falling on bare, ash-covered soil can cause erosion, the washing away of topsoil that took centuries to build. Early researchers noticed that the ash layer, while fragile, actually acts as a temporary shield. It absorbs the first light rains and holds moisture close to the surface. This gives the earliest sprouting plants just enough water to take hold before the ash washes away. It is a narrow window, but it is enough. Scientists also began to document the animals that returned first. They expected large mammals to be the last to come back. They were surprised to find that many small creatures moved into burned areas within hours of the fire passing. Certain beetles, including the black fire beetle, can detect the heat and smoke of a wildfire from miles away. They fly toward the fire, not away from it, arriving while the ground is still warm to lay their eggs in the freshly burned wood. Their larvae feed on the charred timber. These beetles were among the first animals that researchers identified as true fire specialists, creatures whose lives are built around the presence of fire rather than its absence. The study of post-fire recovery also revealed something important about ash itself. Early scientists thought of ash as inert, lifeless material. Chemical analysis showed otherwise. Ash is rich in potassium, calcium, and phosphorus, minerals that plants need to grow. When rain eventually moves the ash into the soil, it acts like a slow-release fertilizer. The burned forest is not starting from nothing. It is starting from a foundation that the fire itself helped to build. All of this knowledge came from the same simple practice: going back, looking closely, and writing down what was there. The scientists who built our understanding of fire recovery were not working with satellites or complex instruments in those early years. They were walking through burned forests with notebooks. They were counting seedlings. They were digging small holes in the soil and looking at what lived there. They were patient, and the land rewarded their patience with answers. What they found over decades of careful study was that the first days after a wildfire are not a pause before recovery begins. They are the recovery. The process starts in the hours after the last flame goes out, in the ash and the bare soil, and the seeds waiting just The forest does not mourn what the fire took. It begins immediately and without hesitation to build something new. What grows back first is not what you might expect. Most people picture a burned forest and imagine that trees return first, that the tall pines and oaks slowly push back up from the ground and reclaim the space. But that is not what happens. The very first living things to move into a burned area are almost invisible. They are fungi and bacteria working quietly in the soil. Within days of a fire, microscopic life begins to shift and reorganize beneath the surface. These tiny organisms start breaking down the charred material left behind. They begin rebuilding the underground networks that larger plants will eventually depend on. Then come the mosses and the lichens. Lichens are a strange and wonderful partnership between fungi and algae. Two very different organisms living as one. They spread across bare rock and burned soil in thin, flat sheets of gray and green. They are often the first visible sign that life is returning. They do not need much. A little moisture, a little light, and they begin to grow. Slowly, they help break down the surface of rocks and add organic matter to the soil. They are preparing the ground for everything that follows. After the lichens come the wildflowers. This is one of the most surprising things scientists have documented about post-fire recovery. In the first spring after a major wildfire, burned hillsides often explode with color. Fireweed is one of the most famous examples. Its bright pink and purple flowers appear so quickly and so reliably after fires that it has become a symbol of renewal in many parts of the world. Fireweed seeds are incredibly light. They carry tiny white hairs that let them float on the wind for miles. They find bare, open ground and take hold fast. A burned hillside that looked gray and lifeless in October can be covered in tall pink flowers by the following July. The speed of this recovery is genuinely surprising. Scientists studying forests after the 1988 Yellowstone fires expected the recovery to take many decades. What they found instead was that within just 2 years, more than 90% of the burned area showed signs of new plant growth. The forest forest was not recovering slowly. It was rushing back. The open canopy, with no tall trees blocking the sunlight, meant that the ground received more light than it had in years. Seeds that had waited in the soil for exactly this kind of opening finally had their chance. Some plants do not even need seeds to come back. Many shrubs and trees in fire-prone regions have a remarkable ability to resprout from their roots. The root system survives underground, protected by the soil from the heat of the fire above. When the flames pass, the roots are still alive. Within weeks, new green shoots push up from the base of what looks like a dead, blackened stump. The plant does not have to start over from a seed. It already has a deep, established root system, pulling water and nutrients from the soil. These resprouting plants often grow faster in the first year after a fire than they ever did before. Oak trees are especially good at this. Many species of oak can resprout vigorously from their root crowns. The thick woody base just at or below the soil surface. A large oak that burns down to a blackened trunk can send up dozens of new green shoots within a single growing season. The tree looks destroyed, but underground it is very much alive, and it is already working. There is something else that surprises people about post-fire forests. They are often louder than the forests that came before. The open ground and the new growth attract insects in enormous numbers. Those insects attract birds. Woodpeckers in particular are drawn to burned forests, where dead standing trees, called snags, are full of beetle larvae. Black-backed woodpeckers are so closely tied to burned forests that scientists consider them a fire-dependent species. They need burned forest to survive. Without periodic fire, their habitat disappears. The burned forest, then, is not a place of absence. It is a place of unusual richness. It holds species that cannot live anywhere else. It supports life that the dense, shaded forest before it could not. The fire removed what was there, yes. But in removing it, the fire created something that the old forest never was. Wide open, full of light, rich in minerals, and ready for a rush of new life that moves faster and stranger than most people ever imagine. The land does not wait to be coaxed back. It comes back on its own terms, in its own order, and often in ways that leave the scientists watching it quietly amazed. Smoke rises long before the fire is gone. It climbs in great gray columns, sometimes reaching miles into the sky, and then it spreads. It thins and flattens and drifts. And in that drifting, it begins a journey that touches systems far beyond the forest where it was born. Wildfire smoke is not simply ash and air. It is a complex mix of tiny particles and gases. Scientists call the smallest of these particles fine particulate matter, or PM25. These particles are so small that 20 of them lined up side by side would not equal the width of a single human hair. They are light enough to stay suspended in the air for days, sometimes weeks, and they travel. A large wildfire can push smoke across an entire continent. This has been measured and confirmed many times. Smoke from wildfires in the western United States has been tracked drifting all the way to the eastern seaboard, more than 2,000 miles away. Smoke from fires in Siberia has crossed the Pacific Ocean and reached North America. Smoke from Australian wildfires has circled the globe. The air above a city with no fires nearby can still carry the chemical fingerprint of a forest that burned thousands of miles away. That reach has real effects on the people and places the smoke passes over. Fine particles from wildfire smoke irritate the lungs. They can worsen asthma and other breathing conditions. During large fire seasons, hospitals in cities far from any active fire see a rise in emergency visits for respiratory problems. The smoke does not stay in the wild. It moves into the places where people live, and it carries the fire's chemistry with it. But smoke does something else, something quieter and stranger. It changes the light. When thick smoke fills the sky, it scatters sunlight. The sky turns a deep, heavy orange or a pale, washed-out yellow. The sun itself can appear as a dull red disk, its edges soft and blurred. This is not just a visual effect. The smoke filters out certain wavelengths of light, the blue and violet end of the spectrum, and lets the longer red and orange wavelengths pass through more easily. People who have lived through a heavy smoke event describe the light as eerie. like late afternoon, even at noon, like the whole world turned amber. This filtering of sunlight has measurable effects on temperature. Thick smoke can reduce the amount of solar energy reaching the ground, cooling the surface slightly beneath the heaviest plumes. At the same time, the smoke absorbs heat in the upper atmosphere. The result is a kind of layering, where the air near the ground cools, while the air higher up warms. This changes how air circulates, and it can affect local weather patterns for days at a time. Smoke also interacts with clouds. The tiny particles act as seeds around which water droplets can form. Scientists call these seeds cloud condensation nuclei. When smoke floods the atmosphere, it creates enormous numbers of these tiny seeds. Clouds that form in smoky air tend to have more smaller droplets rather than fewer larger ones. Smaller droplets are less likely to fall as rain, so heavy smoke from wildfires can actually suppress rainfall in the regions it drifts over, at least temporarily. The fire, in burning, can reach out and touch the water cycle of places it never came close to. There is something almost hard to believe about that. A fire burning in a forest sends smoke drifting over a distant city. That smoke seeds the clouds above the city with tiny particles. Those clouds hold their rain a little longer than they otherwise would. The fire and the rain, separated by 1,000 miles, are still in conversation with each other. Smoke also carries nutrients. Ash and fine particles from burned vegetation contain nitrogen, phosphorus, and other minerals. When smoke drifts over the ocean, and those particles eventually settle onto the water's surface, they fertilize the upper layer of the sea. Studies have found that large wildfire events can trigger blooms of phytoplankton, the microscopic plant-like organisms that form the base of the ocean food chain. In ocean regions downwind of major fires, the forest burns on land and the sea responds. Everything connects. The smoke that stings the eyes of someone standing in a city park, the orange light that makes a photographer stop and look up, the rain that holds back just a little longer than expected, the bloom of green life spreading across a distant patch of ocean. All of it traces back to a single fire burning in a single forest. The reach of a wildfire does not end at the edge of the flames. It extends outward, invisibly, into systems that seem to have nothing to do with fire at all. Fire does not just change the land, it changes the water too. When a wildfire burns through a forest, it removes something that most people never think about: the canopy. Those tall trees, with their broad leaves and thick branches, catch enormous amounts of rain before it ever reaches the ground. A healthy forest can intercept a significant portion of rainfall, holding it up in the leaves and letting it slowly evaporate back into the air. When the trees are gone, all of that rain falls straight down. It hits bare soil with nothing to slow it. That bare soil has another problem. Intense heat from a wildfire can actually change the chemistry of the ground itself. The top layer of soil becomes hydrophobic, which means it repels water rather than absorbing it. Scientists call this layer a water-repellent crust, and it forms when certain compounds from burned plants and roots get baked into the soil by extreme heat. Rain that would normally soak in and travel slowly downward now slides across the surface instead. The ground behaves almost like pavement. The result is runoff, fast, powerful, carrying everything with it. Ash, loose soil, charred debris, and sediment all rush downhill together when rain arrives after a fire. This is why burned hillsides are so dangerous in the weeks and months after a wildfire passes through. A rainstorm that would have been gentle and unremarkable in a healthy forest can trigger a debris flow. A fast-moving river of mud and rock on a burned slope. These flows can travel at tremendous speed and carry boulders the size of cars. The water that does make it into streams and rivers after a wildfire carries a heavy load. Ash contains nutrients, but it also carries contaminants. Burned structures, vehicles, and industrial materials release chemicals into the runoff. Studies of watersheds after major wildfires have found elevated levels of heavy metals, nitrogen compounds, and other substances in nearby waterways. Fish and other aquatic life can be harmed. Drinking water sources sometimes require treatment. The fire is long gone, but its chemistry lingers in the water for months, sometimes years. even here, the story is not simply one of damage. Burned watersheds change their behavior in ways that scientists are still working to fully understand. Some burned areas, after the initial surge of dangerous runoff, actually begin to deliver more water to streams over time, without trees pulling moisture up through their roots and releasing it into the air through their leaves, a process called transpiration. More water stays in the ground and eventually flows into rivers. Some river systems in fire-prone regions actually run higher in the years following a large burn. The fire, in a strange way, gives the water back. Snowpack is part of this story too. In mountain forests, trees shade the snow on the ground, slowing how fast it melts in spring. When fire removes that shade, snow in burned areas melts earlier. This shifts the timing of water delivery to rivers and streams. In regions that depend on a slow, steady release of snowmelt through spring and early summer, an earlier melt can mean rivers run high and fast in April, and then run low and dry by July. Communities and ecosystems that depend on that steady flow feel the shift. The water cycle, that ancient and patient system of evaporation, cloud formation, rainfall, and flow, does not stop when a fire burns through. It keeps moving, but fire bends it. It speeds some parts up and slows others down. It changes where water goes, how fast it travels, and what it carries with it. A single large fire can alter the hydrology, the way water moves through a region for a decade or more. There is something humbling about this. Water and fire seem like opposites. One puts the other out, but they are deeply connected. The health of a forest shapes how water moves through the land. The movement of water shapes whether a forest grows dry enough to burn. Fire clears the land, changes the soil, shifts the snowmelt, and redirects the rivers. Rain returns slowly and begins to restore what was lost. The soil heals, the roots return, the canopy grows back, leaf by leaf, and once again begins to catch the rain before it falls. The water cycle and the fire cycle are not separate things. They are two rhythms in the same slow, patient process. The land breathes in fire and breathes out water. It has been doing this for millions of years, and it will or the cold silver of the moon on snow. Fire makes a warm, orange, flickering light. It dances. It moves. And when a wildfire burns across a hillside at night, that light is visible from space. Satellites orbiting hundreds of miles above the Earth can see the glow of a large wildfire the way you might see a candle through a dark window. That glow is not just light. It is carbon released back into the sky. Carbon is one of the most important elements on Earth. It is the building block of all living things. Every tree, every blade of grass, every root threading through dark soil is made partly of carbon. Plants pull carbon dioxide, a gas made of carbon and oxygen, out of the air. They use sunlight to turn that gas into wood, leaves, bark, and seeds. This process is called photosynthesis. A single large tree can store hundreds of pounds of carbon inside its trunk and branches over its lifetime. A whole forest stores an enormous amount. When fire burns that forest, the carbon does not disappear. It changes form. The wood breaks apart. The carbon that was locked inside the tree for decades gets released back into the air as carbon dioxide and other gases. A large wildfire can release as much carbon dioxide into the atmosphere as millions of cars do in an entire year. Scientists have measured this carefully, and the numbers are striking. Fire is one of the fastest ways that carbon moves from the land back into the sky. But here is what makes this story more than just loss. The carbon cycle, the slow movement of carbon between the air, the land, the ocean, and living things, is not a straight line. It is a circle. And fire is one of the things that keeps it turning. When a burned forest begins to grow back, the new plants start pulling carbon out of the air again. Young trees and fast-growing shrubs are hungry for carbon. They absorb it quickly. A recovering forest can pull carbon out of the atmosphere at a faster rate than an old, mature forest. The young trees are growing fast, building new wood, storing new carbon. Over decades, the forest slowly refills. The carbon that fire released begins to return to the land. Not all of the carbon from a fire goes back into the air as gas, though. Some of it becomes something else entirely. When wood burns without enough oxygen, it does not fully combust. It turns turns into charcoal, a dark, porous material that scientists call biochar. This charcoal can last in the soil for thousands of years. It does not break down quickly. It holds carbon in place, locked into the earth, long after the fire is gone. Ancient soils in many parts of the world still contain charcoal from fires that burned thousands of years ago. That carbon has been sitting quietly underground ever since. This charcoal does something else too. It improves the soil. It holds water. It creates tiny spaces where microbes, the microscopic living things that break down dead material and release nutrients, can live and thrive. Some scientists believe that ancient peoples in the Amazon basin deliberately added charcoal to their soil to make it more fertile. The result was a dark, rich earth called terra preta, which means dark earth in Portuguese. It is still some of the most productive soil in the region today. The light of a wildfire, then, is not only destruction, it is transformation. Carbon that spent decades locked inside a tree is suddenly free, rising into the sky in smoke and heat, glowing orange against the dark. Some of it drifts high into the atmosphere and circles the globe. Some of it falls back to Earth as ash, rich with minerals. Some of it becomes charcoal and sinks into the soil, where it will stay for centuries. The sky above a wildfire has its own strange colors. The smoke turns the sun red and the moon orange. Fine particles scatter the light in ways that shift the whole palette of the sky. Photographers and scientists alike have noted how the light during a major fire event feels different, softer in some ways, harsher in others. The air itself carries the story of what burned. Carbon moves through the world in ways we are still learning to understand. Fire is one of its oldest and most powerful drivers. It has been releasing and reshaping carbon on this planet for hundreds of millions of years. Long before humans arrived, fire and carbon were already in conversation. The land burns. The carbon rises. The forest returns. And the cycle begins again, patient and steady, lit by its own slow glow. Some places on Earth burn more than others. The land itself, the climate, the plants, the wind, all of it comes together in certain corners of the world. Australia is one of the most fire-prone places on the planet. The continent sits beneath a harsh sun, and much of its interior is dry for months at a time. The plants that grow there have adapted over millions of years to survive in that heat. Eucalyptus trees, with their long peeling bark and oil-rich leaves, are almost designed to burn. The oils inside those leaves are so flammable that eucalyptus forests can produce their own clouds of vapor that catch fire before a flame even touches the tree. During Australia's Black Summer fires of 2019 and 2020, more than 18 million hectares burned. That is an area larger than many countries. The sound of those fires was something witnesses described again and again. A deep, low roar, not the sharp crack of a single log splitting in a campfire, but something vast and continuous, like a freight train that never arrives and never leaves. The fire creates its own wind as it burns, and that wind feeds back into the flames, and the flames grow louder, and the roar deepens. People miles away reported hearing it before they could see any smoke. The Mediterranean region is another place where fire returns reliably each year. Southern France, Spain, Greece, Portugal, and the hills around the Mediterranean Sea share a climate that is warm and wet in winter, then hot and bone dry in summer. The shrubby, low-growing plants of that region, called maki, dry out completely by July and August. They become fuel waiting for a spark. Greece has experienced some of the most devastating fires in European history, with flames racing through hillside villages and reaching the edges of the sea. California sits in a similar climate zone, and it burns in a similar rhythm. The state's fire season has stretched longer and longer in recent decades. The Santa Ana winds, which blow hot and dry from the inland desert toward the coast each autumn, arrive just as the land is at its driest. They push fires at extraordinary speeds across canyons and ridges. The sound of a fire driven by Santa Ana winds has been described as a hollow, rushing howl. The wind and the fire so tangled together that you cannot tell where one ends and the other begins. The savannas of sub-Saharan Africa burn on a scale that is almost hard to picture. Vast stretches of dry grass, sometimes hundreds of miles wide, catch fire each dry season. Scientists estimate that Africa accounts for roughly 70% of the world's burned area in any given year. These fires are often lower in intensity than forest fires. They move through grass rather than towering trees, but their scale is immense. From space, satellites track the orange glow of African savanna fires as they sweep across the continent in slow, enormous arcs. The boreal forests of Canada and Russia, the great cold forests that circle the top of the northern hemisphere, are also burning more often. These forests are made of spruce, pine, and fir trees that hold enormous amounts of carbon in their wood and in the frozen soil beneath them. When they burn, they release that carbon in great pulses. The fires in these forests tend to be intense and fast-moving. The sound is different here, sharper and higher, the resin in the conifers popping and hissing as the heat reaches them. A sound like something electric, like the forest is crackling with its own energy. Indonesia experiences a different kind of fire entirely. There, fires often burn not just the surface, but the peat beneath it. Peat is compressed, ancient plant matter, layers of it built up over thousands of years in swampy ground. When it dries out and catches fire, it burns slowly and deep, smoldering underground for weeks or months. The smoke it produces is thick and low and spreads across entire regions. The sound of a peat fire is almost no sound at all. A quiet, steady release of smoke from the ground, barely visible at first, the earth itself burning from within. Each of these places has its own fire voice, its own rhythm of burning, its own season of smoke and heat, but they are all part of the same story, the story of a planet where fire is not an accident. It is a feature. It has always been here, sounding its low and ancient note across every continent, in every climate, in every age of the world. And long before scientists began measuring fire behavior with instruments, long before satellite maps tracked smoke across continents, human beings already understood fire deeply. They had learned it the slow way. Over thousands of years, through careful watching, through seasons of burning and seasons of rest, through knowledge passed from elder to child in languages that held the land inside their words. Indigenous peoples around the world developed fire management practices that are, when you look at them closely, extraordinarily precise. Not precise in the way of equations written on paper, precise in the way of a system tested across hundreds of generations, refined until it worked, kept alive because it worked. In Australia, Aboriginal peoples have practiced what is often called cultural burning for at least 50,000 years. That number is worth sitting with for a moment. 50,000 years. That is longer than any written record on Earth. It is longer than the oldest known cave paintings. These communities were reading fire and land together across a span of time almost too large to picture. Their burns were small and deliberate. They chose specific times of year, specific weather conditions, specific patches of land. They burned in cool seasons when the air held a little moisture, when the fire would move slowly and stay low. This kept the burns gentle. It cleared out the dry undergrowth without killing the larger trees. It created a patchwork of burned and unburned land, a mosaic of different habitats that supported more kinds of animals and plants than a single unburned stretch ever could. Scientists studying these patterns now have a name for this kind of landscape. They call it pyrodiversity, meaning a variety of fire histories across a region. Evidence suggests that high pyrodiversity supports high biodiversity. More kinds of fire history means more kinds of habitat. More kinds of habitat means more kinds of life. The Aboriginal burning practices created exactly this across an entire continent for tens of thousands of years. The knowledge was not written down. It lived in ceremony, in story, in the names of places, in the timing of seasonal practices. It was a living library carried in people. And when colonization disrupted those practices across Australia, the land began to change. Undergrowth built up. Dry fuel accumulated. The careful patchwork of small burns gave way to decades of unburned land, and then to the kind of catastrophic fires that tear through everything at once. Indigenous fire knowledge was not primitive. It was sophisticated in ways that took modern a long time to recognize. In North America, many native nations also used fire as a land management tool for thousands of years. The Karuk, Yurok, and Hupa peoples of what is now Northern California burned regularly to maintain prairies, encourage the growth of specific plants used for food and basket weaving, and keep forests open and healthy. The Coast Miwok burned coastal grasslands. The Anishinaabe burned forest edges around the Great Lakes. Across the continent, fire was a tool, a relationship, a responsibility. These practices shaped the landscapes that European explorers later described as wild and untouched. The open oak woodlands of California, the vast grasslands of the interior, the rich and varied forests of the Pacific Northwest. Much of what looked like wilderness was, in fact, tended land. Land shaped by thousands of years of careful burning. The mathematics here is quiet but real. A small burn conducted at the right time, in the right conditions, might consume a few acres and move slowly for a day. That same fuel, left to accumulate for 20 or 30 years, can feed a fire that moves at 60 miles per hour and consumes hundreds of thousands of acres in a week. The difference between those two outcomes is knowledge, timing, relationship with the land. Today, fire scientists and land managers are working alongside Indigenous communities to bring cultural burning back. In Australia, Aboriginal rangers now conduct cool burns across national parks and conservation areas. In California, the Karuk and Yurok tribes have been working for years to restore their burning practices, and state agencies have slowly begun to recognize the value of what they are doing. The knowledge was never lost. It was waiting. There is something deeply moving about this. The oldest fire knowledge on Earth, carried through oral tradition across thousands of generations, now being confirmed by satellite data and ecological research. The elders knew what the instruments are only beginning to measure. They knew that fire, used with care and understanding, does not destroy the land. It tends it. It keeps it in balance. It is part of the agreement between people and place, an agreement written not in numbers, but in smoke and season and the slow turning of years. is burning, the people who fight it are not simply reacting. They are reading. Every firefighter on the line is watching the same things a fire has always responded to: fuel, wind, and terrain. These three forces are always in conversation with each other. A firefighter who understands that conversation can predict where a fire is going before it gets there. The men and women who work on the front lines of a wildfire are called wildland firefighters. They train for months to learn how fire behaves. They study slope and wind direction. They learn to read the color of smoke. Dark black smoke often means a fire is burning hot through heavy fuel. Light gray or white smoke can mean the fire is slowing, moving through thinner material, or losing energy. The color of the smoke is a message. Experienced firefighters know how to receive it. One of the most important tools a firefighter carries is a weather forecast. Fire weather forecasters work alongside fire crews, tracking wind shifts, humidity levels, and temperature changes hour by hour. A sudden drop in humidity can turn a manageable fire into something far more dangerous within minutes. A wind shift can send a fire racing in a new direction, cutting off escape routes. Firefighters are trained to always know where their safety zones are and where their exit paths lead. These are not suggestions. They are survival rules. Firefighters use a set of guidelines called the 10 Standard Firefighting Orders, a list of behaviors developed after deadly fires in the mid-20th century. These orders cover everything from keeping watch on the fire at all times to never fighting a fire without a safe escape route. They exist because fire is fast and unpredictable, and the margin for error in the field is very small. The history of wildland firefighting is also a history of learning from tragedy. One of the most powerful tools in a firefighter's approach is the fire line. A fire line is a strip of ground cleared of all fuel, dug down to bare mineral soil that a fire cannot cross. Crews build fire lines by hand using tools called Pulaskis and McLeods, scraping away brush, grass, and leaf litter. A Pulaski is a two-headed tool, part axe and part hoe, designed specifically for this work. Building a fire line by hand is exhausting physical labor. A crew might spend an entire night digging a line through steep, rocky terrain, working in the dark by headlamp, trying to stay ahead of a fire moving toward them. Aircraft play a large role in modern wildfire response. Air tankers drop fire retardant, a thick red chemical mixture that slows the spread of fire by coating fuel and making it harder to ignite. Helicopters carry water in large buckets, making repeated drops on hot spots and active flame fronts. Aerial observation planes fly above the fire, giving commanders a view of the whole situation that no one on the ground can see. The coordination between air and ground crews is careful and constant. Incident commanders, the people who manage large wildfire operations, use a system called the Incident Command System to organize hundreds or even thousands of people working across a single fire. This system was developed in California in the 1970s after a series of fires revealed how difficult it was to coordinate multiple agencies with different communication systems. Today, it is used not just for wildfires, but for hurricanes, floods, and other large emergencies around the world. A tool born from fire now helps manage almost every major disaster response. There is something remarkable about the balance that firefighters must hold. They are not trying to eliminate fire from the land. They understand, as the indigenous communities before them understood, that fire belongs here. Their work is not to stop fire entirely, but to protect lives and communities while letting the land keep some of its natural rhythm. The goal is not zero fire. The goal is the right fire in the right place at the right time. This is a fragile balance. The conditions that make it possible, the knowledge, the resources, the coordination, the weather windows that allow safe burning, are all precise. Remove one element, and the whole system shifts. A drought year with no safe window for controlled burns means fuel builds up. Fuel that builds up feeds larger fires. Larger fires are harder to fight and more dangerous for the crews who face them. Every variable matters. Every season counts. The firefighter standing on a ridge at dawn, watching smoke rise from a valley below, is doing something ancient. They are reading fire. They are deciding how to respond to one of the oldest forces on Earth. And in that moment, they carry the weight one of the most powerful tools a land manager carries is not a shovel or a hose. It is a match. Controlled burns, sometimes called prescribed burns, are fires set on purpose. Land managers light them deliberately under carefully chosen conditions to reduce the fuel that wild, unplanned fires feed on. The idea sounds strange at first. Fighting fire with fire. But it is one of the oldest and most effective tools humans have ever used to care for the land. The science behind it is straightforward. When dead leaves, dry brush, and fallen branches pile up on a forest floor over many years, they become a deep layer of waiting fuel. A spark from lightning or a power line can turn that fuel into a catastrophic fire. A controlled burn clears that layer away. It removes the fuel before a dangerous fire can use it. Think of it like clearing out a room before a flood arrives. Less material means less damage. Prescribed burns also do something else. They return nutrients to the soil. When organic matter, the leaves and branches and plant debris, burns slowly at low heat, it breaks down into ash. That ash settles into the ground and feeds it. Grasses and wildflowers often return within weeks of a controlled burn. Bright green shoots pushing up through the dark, charred earth. The land does not mourn the fire. It responds to it. But setting a controlled burn is not as simple as striking a match. Land managers must wait for what they call a prescription window, a narrow set of conditions where the fire can be managed safely. The humidity must be high enough that the fire won't spread too fast. The wind must be present enough to carry smoke away, but not so strong that it pushes the fire out of control. The temperature, the moisture in the soil, the dryness of the vegetation, all of these must fall within a specific range at the same time. These windows can be rare. In drought years, they may not come at all. When conditions are right, crews prepare carefully. They build containment lines, cleared strips of bare earth that stop the fire from spreading beyond its intended area. They monitor wind direction constantly. They keep water and equipment nearby. A prescribed burn that escapes its boundaries becomes a wildfire. The margin for error is small, and the people who manage these burns know it. In the United States alone, land managers conduct hundreds of thousands of acres of prescribed burns each year, the U.S. Forest Service, the National Park Service, and state agencies all use this tool regularly. In the southeastern United States, longleaf pine forests have been managed with frequent low-intensity fire for generations. These forests depend on it. Without regular burning, shrubs crowd out the pines, and the open, grassy understory disappears. The whole ecosystem shifts. Australia has some of the most aggressive prescribed burning programs in the world. After devastating fire seasons, particularly the catastrophic fires of 2019 and 2020 that burned more than 46 million acres, there has been renewed focus on using controlled burns to reduce fuel loads before the dry season arrives. The challenge is enormous. The land is vast. The conditions are unpredictable, and the window for safe burning grows shorter as temperatures rise. Here is where the open questions live. Scientists and land managers are still working to understand exactly how much prescribed burning is needed, and where, and how often. They are studying how smoke from controlled burns affects air quality in nearby communities. They are asking whether the benefits of burning in one area can offset the risks of smoke exposure for people with respiratory conditions who live downwind. These are real tensions, and they do not have simple answers yet. There is also the question of scale. Many researchers believe that the current pace of prescribed burning in the United States is far too slow to keep up with the fuel that accumulates each year. Some estimates suggest that millions more acres would need to be burned annually just to bring fuel loads down to a manageable level. The gap between what is needed and what is currently possible is significant. And yet the direction is clear. More and more, the science points toward fire as a necessary part of the land's health, not an enemy to be eliminated. The forests evolved with fire. The soil expects it. The seeds of certain plants wait for it. The question is not whether to use fire. The question is how to use it wisely, at the right scale, with the right knowledge, in the right places. The match is not the problem. It never was. The match, in careful hands, is the beginning of something the land has always known how to finish. use fire more wisely. The world around us is shifting. The conditions that shape wildfires are not the same as they were 50 years ago. They are not even the same as they were 10 years ago. Something larger is changing, and fire is one of the clearest signs of that change. The planet is warming. Average global temperatures have risen by more than 1 degree Celsius since the late 1800s. That may sound small, but for the systems that govern weather, soil, and vegetation, even a fraction of a degree makes an enormous difference. Warmer air holds less moisture. Warmer soil dries out faster. Warmer springs arrive earlier, and warmer autumns linger longer. The window of time each year when fire can spread easily has grown wider in many parts of the world. Scientists call this the fire season. In parts of the American West, the fire season is now roughly 2 to 3 months longer than it was in the 1970s. That means more days each year when the air is dry enough, the wind is strong enough, and the fuel is ready enough for a fire to escape control. More days of risk, stacked one after another, season after season. Drought is part of this story too. As temperatures rise, droughts become more intense and last longer in many regions. Trees and shrubs that might have survived a dry summer begin to die. Dead vegetation does not decay quickly in dry conditions. It stays on the ground or standing in place, slowly becoming fuel. In some forests in the western United States, bark beetles have killed millions of trees that were already weakened by drought. Those standing dead trees are sometimes called ghost forests. They are pale and dry and full of stored energy that fire can release in an instant. The fires that result from these conditions are often larger and more intense than historical fires. Researchers have documented a clear trend. Since the 1980s, the total area burned by wildfires in the western United States has increased significantly. Some studies suggest that human-caused climate change is responsible for roughly half of the increase in burned area in that region over recent decades. The fires are not just more frequent. They are burning hotter, moving faster, and reaching places that rarely burned before. High elevation forests are one example. Subalpine forests, the cool and drying out earlier each year. Fires are now reaching elevations they have not touched in recorded history. The trees there did not evolve with frequent fire. They have no adaptations to help them recover quickly. When those forests burn, recovery is slow and uncertain. The Arctic is another place where fire is expanding into new territory. Permafrost, the layer of frozen ground that underlies much of the far north, stores enormous amounts of carbon that has been locked away for thousands of years. As the climate warms, permafrost thaws. The vegetation above it dries. Fires in the boreal forests and tundra of Alaska, Canada, and Siberia are becoming more common and more severe. When those fires burn deep into the soil, they release carbon that has been frozen since long before humans walked the earth. That carbon enters the atmosphere and contributes to further warming. Fire and climate are feeding each other in a slow, grinding loop. This is one of the more sobering things that scientists are tracking. The relationship between fire and climate is not one-directional. Fire does not simply respond to a warming world. It also shapes the warming world. Every large fire that burns through a carbon-rich forest or peatland sends gases into the air that trap heat. The system is connected in ways that make the future harder to predict and harder to manage. And yet, even here, the story is not only one of loss. Researchers are working to understand these connections more deeply. Fire behavior models are becoming more precise. Satellite systems now track fires in near real time across the entire planet. Communities are beginning to adapt, rethinking where homes are built, how forests are managed, and how fire is incorporated into land stewardship rather than excluded from it. The land is not passive in this story either. Forests that burn and recover sequester carbon again as they grow. Grasslands that burn release carbon briefly, then pull it back down through their roots within a season or two. The earth has its own ways of finding balance, even as the conditions around it shift. The question is whether the pace of change will allow those natural rhythms enough time to keep working. Zoom out now, all the way out. Picture the Earth from space. It It is a small, bright sphere wrapped in thin blue air, spinning slowly in the dark. From that distance, you cannot see the fires burning across its surface, but they are there. They have always been there. Fire has been part of this planet's story for at least 420 million years. Scientists know this because they have found ancient charcoal pressed into rock, the blackened remains of forests that burned long before any human being ever walked the land. Fire is not new to Earth. It is one of Earth's oldest companions. For most of that time, fire and life found a kind of rhythm together. Plants evolved to burn. Animals evolved to survive burning. Soils evolved to recover. The planet learned over millions of years how to carry fire without being consumed by it. That balance was never perfect. There were periods when fires burned far more than they do today, and periods when they burned far less. The oxygen levels in the atmosphere shifted. The climate shifted, and fire shifted with them. We are living through one of those shifts right now. Scientists who study fire across long stretches of time call this field paleofire research. They look at layers of charcoal buried in lake beds and peat bogs, reading the history of fire the way others read tree rings. What they find is that fire activity on Earth is not random. It rises and falls with temperature, with moisture, with the amount of plant life available to burn. And right now, the signals in those records suggest we are entering a period of higher fire activity than the planet has seen in centuries. But here is something worth holding onto. The Earth has been through high fire periods before. It has come through them. Life has come through them. The forests that stand today are the descendants of forests that burned and returned again and again across deep time. The seeds in the soil carry the memory of fire in their very biology. They have been shaped by it. They are ready for it within certain limits. Those limits matter. The pace of change matters. When fire regimes shift slowly, ecosystems have time to adjust. When they shift quickly, the stress can outrun the recovery. What scientists are watching most carefully right now is not just how much fire there is, but how fast the conditions are changing. A forest that might recover from one large fire every 100 years may struggle to recover if large fires come every 20 years instead? And yet, across all of this, something else is also true. Human beings are not only part of the problem, they are also part of the response. For thousands of years, people around the world managed fire with skill and care. That knowledge was often set aside during the 20th century when fire suppression became the dominant approach. Now, slowly, it is being brought back. Land managers are working with indigenous communities. Ecologists are studying how to reintroduce low-intensity fire to forests that have gone too long without it. The tools are improving. The understanding is deepening. Fire is also pushing human beings to think differently about how we live on the land. Cities and towns are rethinking where they are built and how. Architects are designing homes with fire-resistant materials. Communities are creating defensible space, clearing the dry brush and dead wood that gives a fire its first foothold. None of these changes are simple. None of them are fast, but they are happening. Step back even further now, past the history of human beings, past the age of forests, all the way back to the beginning. The carbon that burns in a wildfire today was once floating in the air of an ancient atmosphere. Before that, it was part of a star. The oxygen that feeds the flame was released by the first photosynthetic life, tiny organisms that changed this planet's air billions of years ago. The minerals left behind in the ash were forged in the cores of stars that lived and died long before our sun was born. A wildfire is not separate from the universe. It is the universe expressing itself through heat and light and transformation. The same forces that fuse atoms in the heart of a star are at work in a quieter way in every burning branch and every glowing ember. The earth has carried fire for hundreds of millions of years. It will carry fire long after we are gone. The question we are living through right now is what kind of fire that will be, and what kind of role we will choose to play in shaping it. That is not a small question, but it is a hopeful one. And so we come to rest here at the end of a long and glowing story. You have traveled through smoke and ash, through ancient forests and recovering hillsides, through the sets them free, and the birds that follow the smoke to find their meals. You have learned that fire is not simply destruction. It never was. Fire is one of the oldest processes on this planet. Long before the first human being ever struck a spark, fire moved through grasslands and forests, clearing away the old and making room for the new. It has been doing this for at least 400 million years. The earliest known fossil evidence of wildfire comes from ancient plant material, charred and preserved in rock, from a time when the continents were still joined together in shapes we would not recognize today. Fire was here before us. It will be here after us. And in that long stretch of time, it has always been a force of renewal. Think about what fire leaves behind. The ash that settles over a burned hillside is rich with minerals. Calcium, potassium, phosphorus. These are the building blocks that plants need to grow. Rain carries them into the soil. Roots find them. Within weeks of a fire, the first green shoots begin to push up through the black earth. Scientists who study post-fire recovery have found that some plant species grow faster and stronger in burned soil than in unburned soil. The fire does not just clear the land, it feeds it, and the animals return. First, the insects, drawn by the warmth of the cooling ground. Then the birds that eat the insects. Then the small mammals that follow the birds. Then the predators that follow the mammals. Life does not wait politely for the land to recover. It rushes in. It is eager. The burned forest is not a dead place. It is a busy one. Even the air carries the story forward. The smoke that rises from a wildfire carries carbon back into the atmosphere, where it will eventually be pulled down again by growing plants. Those plants will one day fall, decay, or burn, and the carbon will move again. It has been moving this way for hundreds of millions of years, cycling through air and soil and living things in a great slow loop that has no beginning and no end. You are part of that loop. Every breath you take contains carbon atoms that have passed through countless living things before you. The earth holds all of this together. It spins slowly through space, tilted at just the right angle to give us seasons, orbiting a star that is just the right distance away to keep liquid water on the surface. The thin shell of air that wraps around this planet holds in just enough warmth to make life possible. And within that thin shell, fire and water and wind and soil all work together in ways that took billions of years to develop. Right now, somewhere on Earth, a fire is burning. It might be a small grass fire in a dry savanna, glowing orange in the late afternoon light. It might be a slow, cool burn moving through a pine forest in the early morning, the smoke rising straight up into a pale sky. Somewhere, a hillside that burned last year is covered in new green growth, soft and bright against the dark soil. Somewhere, a lodgepole pine is releasing its seeds for the first time in decades, because the heat finally came and opened what had been sealed shut. And somewhere, very far from any fire, an ocean is resting under moonlight. The surface moves in long, slow swells. The water is dark and deep and cold, and it holds more life than we have ever fully mapped. Above it, stars are turning in their slow arcs across the sky. The galaxy wheels overhead, unhurried, as it has for billions of years. You are a small, warm creature on a small, warm planet, and you are held by all of it. The fire that worries us and the fire that renews the land are part of the same ancient story. The earth knows how to carry both. It has been doing so for longer than we can truly imagine. Rest now. The planet is still turning. The stars are still burning. The green is still coming back. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet